All right. So yeah, I'm Carl Alexander. You can actually find me on Twitter. My handle is twigpress. I also happen to write on a little WordPress blog at carlalexander.ca. I tend to write about complex or advanced programming topics, as well as some other things like teaching online or system administration. And a bit that's kind of why this little meme here exists. It's not just because I like to party a lot and people are like, oh my God, Carl, you can't. I think I'm just going to say hi and I'm going to get lost now. But who here has read an article from me? Okay, not that many. So that's actually good that I put this slide in. So a common, a common thing with my articles is that they're kind of long and they're advanced, and it's very common for people to not get it the first time through. And it's the same thing with my talks. So I do things a bit differently. So I tend to have a lot of question periods, which we won't have here, but I also write a companion article, which this talk will have. It'll come online next week. It's about 5,000 words. So I thought I picked a small topic, and I was not quite small enough. So let's begin. Who here has said something like this before? Yeah, like myself. It's super common to go back and look at your code and you're like, what happened here? Like, how did this get so messy? I was sure I had everything under control. And the culprit is often software complexity. But when you start off with programming, it's not really a topic that you're familiar with. You're really focused on learning to code, like getting something, creating code that works. Because when you start off, your code doesn't actually work most of the time either, or you forget a semicolon. Who here forgot a lot of semicolons when they started off? Yeah. And we're also not really thinking about our future self. Like, how are we going to maintain this code that we're kind of learning to do? We're not really thinking about that. And software complexity makes that job really hard, which is why I really think that it's a useful concept to know when you're starting off programming, but it's not covered very often. So what is software complexity? Well, software complexity is a measurement. And what we're trying to measure with software complexity is how much does my code interact with other pieces of code? And the complicated thing with complexity is that there's more than one way to measure that. And today we're going to look at two of them. The first one that we're going to look at is called cyclomatic complexity. So that's actually the one that's better known out of all the measurement methods. That's why it's very common for cyclomatic complexity to be used interchangeably with just complexity. But there's multiple ways of measuring that. And what is cyclomatic complexity? Well, it measures the number of linearly independent paths through a piece of code. Like, what does that mean? Like, it's something, you read that the first time and you're like, I have no idea what this means. And if we take like this small function here, so we have insert default value, nothing too complicated. You have mixed, which is the parameter. You check if it's empty. If it's empty, you assign it of just the default value, and then you return it. Well, with cyclomatic complexity, what you want to do with that is you want to create these control flow graphs of that code so that it starts looking something like this. And right now, you have the beginning of your function, and then you have a node where it's true, where it's false. And with cyclomatic complexity, what you're going to do is you're going to count the number of nodes. So we have 4. And then you're going to count what you call edges. And then there's 4 of those. Then you enter them in this fancy formula. And it tells you that there's actually 2 paths in your code. And you can actually see that. You can see that you can go on the left side, you can go on the right side. But really, this is a lot of work. Like, I don't want to be doing that. I don't think none of you here were coming to this talk thinking about that or having to do like drawing graphs of your code. You don't want to do that. So there's an easier way to calculate that. You can just go and look at your code, and let's say you always want to count the initial function. So when you come in the function, that counts as 1, and then each statement counts as one level of complexity. So if we make things a bit more complicated and we add an or statement, so we check if it's a string, if it's not a string, or if it's empty, then you now have a complexity of 3. But what does 3 mean? Whoop, I went a bit too fast. What does 3 mean? Like, what does it mean to have a cyclomatic complexity of 3? Well, if you have a complexity level between, let's say, 1 and 4, that's actually low complexity. Actually, for most of us, we wouldn't look at this code, and we wouldn't even be thinking, oh, is this complicated or not? It's just a small function. It's small functions that you think are trivial, that you won't think too much about. It's really when you start hitting what I call like moderate complexity. So once you start hitting values of 5 or between 5 and 7, at that point, you start seeing brittleness in your code. You start seeing, oh, well, things aren't as simple for me to understand, to read. It's starting to feel like I'm losing control a bit on what my function or my method is doing. And then you have what high complexity, which at 8 or 10, at that point, the function is high complexity. It's still OK. You can still use it. But you should really be on high alert. You should be thinking, oh, my goodness, I should be starting to think about ways of reducing the complexity of that. And then if you work with WordPress, you're probably used to ludicrous levels of complexity, which is when you have a function, that's like 200 lines of code. There's a lot of statements in there. At that point, what you want to do, we'll talk about it a bit, but at those levels of complexity, you're really, really looking to fix those. But this brings us to a certain aspect of cyclomatic complexity that I want to discuss, which is issues with cyclomatic complexity. So one of the issues that you'll run across is that we all work with software here. We know what an if statement is, what a while statement is, what a for loop is, what a switch with case are, but we also know that they're not identical. But cyclomatic complexity considers them to be identical. But for example, if you have a for loop, if you run it once, or you run it 10,000 times, your for loop is the same. Like the code's the same. Obviously, you have performance issues. Like if you're running something 10,000 times, it's going to take a while. But in terms of complexity of your function, it's just a for loop. But we can't really say the same thing about an if statement. Like if you have an if statement in your code, things are changing now. You're not going through the same pattern in your code. Like values are being changed, behaviors different. Those things have different effects on complexity. It also doesn't account for nesting. Who here thinks that a linear for loop is the same as three linear for loops is the same as 3 nested for loops? No, nobody thinks that. I dread to deal with 3 nested for loops. That seems really scary and complicated. And for cyclomatic complexity, it would consider those 2 things the same. So if you have 3 for loops, one after the other, it considers them to be as complex as if you had 3 for loops nested one inside the other. And that's really, really bad. Because what ends up happening is that you're not taking the cognitive complexity of your code into consideration, which, considering I have a bit more time and I cut that section, I'll do a bit of a tangent on it. But one thing that's really important to understand about complexity and versus who here thinks that something that's complex is the same thing as something that's complicated? Okay, it's a trick question. Obviously, they're not the same. It's really important to understand that there's something about code that's hard to read, hard to understand. That's code that's complicated. And code that's complex is often complicated, but they're not the same thing. If I write 5 variables and they're A, B, C, D, E, but there's only one if statement in my code, that code is not complex, but it's definitely complicated to understand. They're not the same, but they're often confused because it's very hard to understand complex code. Like if you have 10 if statements and a for loop in a function, and you're trying to figure out what's happening inside my function, it's very complicated to understand, but you'll figure it out after a while. Like you'll put some var dumps. Who uses var dump for? Hey, yeah. Yeah, put some var dumps in there and figure out, and then maybe a die statement at the end to figure out what's going on. But that's complicated. That's code that's complicated. You're going through it, figuring out what's going on inside of it, but eventually you figure it out and it won't be complicated anymore. Or it'll change with time. One of the things that I like to promote is the idea of being nice to your future self. You know, you write code right now, you're being really clever about it. You're like, oh, I'm so smart. And then you come back to that code 10 months later and you're like, what was I thinking? And so that's an example of complicated, where complicated is the same, it's not the same in time. So cyclomatic complexity doesn't take those facts into consideration. But for us that work with software, that consider, that work daily with it, it's really important when we're trying to evaluate the complexity of our code to take that cognitive complexity in consideration to see whether it's complicated or not. Which is what brings us to the second measurement method that I'd like to talk about, which is called NPAT. And the idea with NPAT is that the NPAT's a kind of an interesting measurement method, because if you try to Wikipedia right now, you're not going to find anything. It's actually just based on a paper from the 80s where the writer highlighted these issues with cyclomatic complexity and tried to figure out another way to measure complexity while solving those shortcomings. And what it does is it counts the number of acyclic execution paths in your code. Again, I don't know why these technical writers choose to use these very complicated names. I'm always like, why? Because what the writer meant is how many unique paths there are inside your code. And this is actually something that's pretty easy to visualize when we start. So if we go back to our insert default value function from earlier, how many different ways are there for us to go through this function? Anybody have an idea? Is there 2? No? 3? 4? No? There are 3 different ways. So the first one, it's if isString is false, then you're automatically assigning the default value to it, and then you're leaving the function. But you also have a scenario where it's saying you have a string, but it's also empty. In that case, you also want to assign a default value. And you have the scenario where it's both a string and it's not empty, so we don't want to assign a default value in that case. So this is pretty easy to visualize so far, but what happens if we add just a bit more? So we add this, we test for an interface called toString interface. And if the object implements that interface, we convert it to a string, but we still do the check after to see if it's a string or if it's empty. So at this point, this is what our graph looks like at this point. So how many paths are there through our code at this point? And we only have 2 if statements now. So how many are we at? So we had 3. So do we have 8, 9, 6? We have 6. And why do we have 6 paths now? That's because things are multiplicative. So it means that as we add paths through our code, those unique paths multiply, so they compound one another. So if we look at the graph here, we have our second half, which we've gone through before, which has 3 unique paths, but our first if statement has 1. It's whether you have the interface or you don't. But because they're in sequence, the whole thing is multiplicative. So you have 2 times 3 equals 6, and that's just how you figure it out. But it's also why conditionals are dangerous. It's actually, I was having, who here follows kind of object calisthenics or like tries to not use else if statements in their code? Okay. So I was having this debate recently about it, and that's one of the reasons why you want to use else if, because if you just separate your if statements, you just created 2 multiplicative scenarios in your code, which makes things go, they increase quickly. That's where it's very, 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 very easy for things to get out of control, because we rarely have 2 conditionals in our code. Like, who here like codes on average 6 if statement in a function? 12? No? But what would happen if we had a dozen? How many unique paths would you have through your code if you had a dozen if statements? Just an if statement, if interface, or something like that. You'd have 4,096 unique paths through your code. And a dozen if statements in a function is not something we're too scared to admit that we have not done. You know, we do this pretty often. It's not uncommon to see that. But it's really, it grows out of control so fast. But how many unique paths through our code should we have? Like, we can all agree that 6, yes, we understand 6, but we don't want to write functions with just 2 if statements in there. Most of the time, tools will warn you at about 200 paths. But between you and me, I can't even come close to visualize 200 different paths through my code. It's a lot. I think in practice, what you're looking for is closer to 50, because 50, you're kind of, like I said, with the complicated, it's a bit complicated, but you'll figure it out pretty quickly, and it still gives you a lot of leeway in terms of the number of if statements or different statements that you want to use in your code. But how do we get to 50? How do we get from 4,096 unique paths to something more reasonable like 50? Well, this is something you've all heard before. You should break large functions. This is 90% of what you're going to have to do to solve these issues, is you want to break your large functions or methods into smaller ones. And to show you the drastic change that this can have is, let's imagine that we have our fictional 12-statement function with its 4,096 paths. What would happen if we went from 12 to 6? How many paths would we have? Well, we'd have 64. So that's huge. It's a huge difference. And that's why that's like the #1 solution or way to manage complexity, is because just removing statements from your code has a it compounds this in the same way that it compounds for increasing the complexity of your function, it compounds on reducing it. The problem here is that it's not easy to split a function into two right down the middle. We can't do that. It's more common to try to find small blocks of code that you want to extract out. So what code is good to extract? Well, this is pretty intuitive, but it's like code that logically belongs together. So I have an example here where I want to create a reminder with a date, but I want to validate that the date follows a specific format. So I have my date format. I use the datetime object to create a formatted date. And then I just check if the format matches. The date I was given matches the formatted date. And if it's not, I throw an exception. Well, we can split that into two. So we can just say, well, is my date empty? Or is, and then you can just check if my date is valid. And then you just create a separate function for that. So that's very straightforward. We're all used to doing that. So this, for example, before you would have had 4 paths, and then you would have 3 paths. So that's still a 25% drop just through that. Another thing that you can do is if you have large conditional statements. So this is really common for us, especially as WordPress developers. A lot of how WordPress works is with arrays. So we're used to checking, okay, is the array empty? Is it an array? Is the value that I'm looking for in there? There are ways to just combine that, and then you can just do something like, does my response have the specific status header that I'm looking for? And then you end up with something like this. And that's a lot simpler and less complex because you went from 3 conditions to 1. The other thing that you can do is, as I alluded earlier, is you can combine conditionals together. So if you have like our previous example of the default value with the instance, if you just assume that it will always give you a non-empty string, you can just combine these 2 functions together with an else if statement. And because of that, you now have just 1 condition. So you lose the multiplication. So instead of having 6 paths, you have 4. So you just dropped everything by 33%. So that's really, really powerful. But a common question you might have is, am I just hiding the problem by doing that? Like, what's the benefit of having this code separated into its own function instead of just leaving this whole mess together and not dealing with it and just sweeping it off the rug? Well, first of all, the whole point of complexity measurement is to really do it at the function and method level. You're not trying to evaluate the complexity of your software. You're not trying to evaluate the complexity of WordPress as a whole. But one thing that's important to keep in mind is that there is a correlation between the two. If you have everything in your code is simple, which means not complex. So if everything's not complex in your code, it's easier to see how the little pieces fit together, and it makes your code, your application less brittle. So what are tools that you can use to do that? Because I don't want to draw graphs. I had to draw graphs for this presentation. I did not enjoy spending hours drawing graphs for this presentation. I don't want to have to do it for every functions and method in my code. This is impractical. So you need tools to scan your code and tell you, okay, here is a function that's very complex. You should look at reducing the complexity in whichever way that you feel comfortable doing, most likely by breaking it down into multiple functions. So the first set of tools that you can use is what we call command line tools. So they're a really good starting point because you can just run them locally. You can just get a feel for it. You can just run it through your entire code, fix things, and just slowly improve the quality of your code because of it. You have two options in terms of command line code. You have PHP code sniffer. So who here uses PHP code sniffer? Yeah, it's pretty common because it's used for enforcing coding standards, which there's a bunch of sniffs for WordPress coding standards. So that's why it's very popular. But it also includes ways to detect cyclomatic complexity. So it won't measure NPAT, which I find is a much more intuitive way of measuring it, but at least it will spot weak points in your code for you. The other one is called PHP mess detector. Who here uses that one? Yeah, there's less people. It's not as well known. It's really, this one's a tool dedicated for really the quality of your code. So it detects issues with your code and warns you about them. Not just complexity issues, like it can be long variable names, short variable names, short function names, long function names, you name it. But what's interesting about it is that it supports both measurement methods. So it supports both cyclomatic complexity and NPAT. But regardless of what you pick and choose, you should actually consider using both because they're both complementary command line tools. So if you're looking to improve the quality of your code and add tools to your toolkit, you should consider using both of them. The other set of tools that you want to use and that I'm more familiar with is what we call code quality services. So these tools are good for teams. So they're SaaS products that connect to your Git repository, and they continuously analyze your code. So each time you do a pull request, each time you do a commit, it'll run a battery of tests. And what this does is that it enforces code quality really at the institutional level. So if you're a company or an agency, you're more interested in those things, in those tools, because they'll force your entire team to code in a way that enforces those code quality requirements, which include complexity. So there's three tools that you can use, three services that you can look at for code quality, because most of them are popular, but PHP, unfortunately, is not a popular language. I don't know why I love PHP, but it's not the most popular programming language, so not every code quality service supports PHP. But Codacity does, CodeClimate, and Scrutinizer. I use Scrutinizer, but they all offer a free tier for open source projects, so you can use whichever one you want. But if you're looking to pay for it, Scrutinizer is a bit cheaper because the other two pay per seat. So you pay a certain amount per person per month. So to conclude, the idea of complexity isn't that complex. And the point of this talk was to show the theory, because it's often seen as a very intimidating topic. As we saw, they use most of the researchers, the computer scientists that developed these measurement methods used very, very scientific language that can seem intimidating, but really is quite simple. And the theory itself isn't that complicated, especially for NPAT, because you're really just about just looking at how many ways there are to navigate your code. It's a bit like your choose your own adventure, those choose your own adventure books. You're just like kind of navigating, oh, what if I choose true here instead of false? What's going to happen next? So NPAT's much more intuitive because of that. It's just harder to represent. That's why I had to do all these node graphs, but I never draw node graphs for that. But really, the only takeaway you need to have is that it's really about the size of your functions and methods. The mathematics that we saw or that we discussed are really there to quantify the effect of complexity, but they're not necessary for you to understand or to reduce complexity in your own code. All that you need to do is just focus on keeping your functions or methods small, and you'll be well on your way to writing higher quality code. Thanks. 5 seconds.